Okay, so I put together all of the takeaways from all the things so we can go over them, and any ones you have questions on, we can talk more about.
All right.
So as I mentioned, the exam questions are broken up into 10 sub-elements, and each sub-element may have anywhere from 2 to I think 6 groups, and there's 35 total groups, so you'll have one question from each group, and the group is typically 8 to, I think there may be some that are up to 14 questions in a group, so you're kind of looking around, probably average around 10 or so.
How long does the exam run usually? A couple of hours?
Most people finish in 20, 25 minutes.
Oh, wow.
35 questions. So some of the basic stuff that you probably have forgotten of the definitions, where current that we measure in amperes is 1 coulomb per second. And a coulomb is a whole bunch of charges. 6.24 times 10 to the 18th, but you don't have to remember that. You need to remember that direct current always flows in one direction, positive to negative, as far as conventional current's concerned. Electron flow is negative to positive. And sometimes that confuses people because Benjamin Franklin got it wrong a long time ago. And alternating current means that it changes direction per cycle. In other words, it has to actually go from positive to negative and negative to positive. It's not the same as it just increases and decreases. It actually has to cross zero. The force that actually causes current to flow, which we measure in volts, is called the electromotive force, or EMF, which is why we use the letter E to represent that force. So that's what you see in the equations, like for Ohm's law and things. We measure frequency in hertz, named after Heinrich. So it's a proper name. That's why it's a capital H, little z. There is a test question about that. It's kind of tricky because they'll show it with a capital and without a capital.
Oh.
Resistance is the opposition to current flow, regardless of whether it's AC or DC. And we measure that in ohms, named after another old German. Remember that conductors are typically metals that have many free electrons, so they allow current to flow, really electrons to flow. And insulators are the opposite. They're non-metal atoms that have very tightly bound electrons in their valence shell, so there are no free electrons running around in an insulator. Any questions on those definitions?
Not so far.
Okay. Okay, Ohm's law. You remember Ohm's law? And remember the little pie chart if you can't remember it. You just draw a circle, divide it in half, divide one of the halves in half.
Oh, yeah.
Label EI and R, where E represents the electromotive force, which we measure in voltages. I stands for current. And I actually can't remember why I was chosen. I suspect because C was already used for capacitance and the speed of light. So they had to pick something different. And R for resistance. They could have used O for opposition, but they didn't. All units of resistance or impedance, which we'll talk about later, are measured in ohms. And sometimes you'll see it represented with a little kind of horseshoe symbol, which is the Greek omega. We can have series and parallel circuits. In the case of a series circuit, where everything is connected together in a sequential string, you'll have the same current flowing through all the components. The voltage across each component may be different. If it's a parallel circuit, where all the components are connected in parallel, the voltage will be the same across all of them, but the current through each component may be different. Any questions on those?
No.
Because if you remember that, you should be able to get the questions right. Now, you may get a question on actually calculating Ohm's law, but all you have to do is remember the formula. And I would suggest you're allowed to write on the back of your answer sheet. You can't bring notes and things with you, but you can write on the back of the answer sheet.
Okay.
If you have trouble remembering that, I would say the first thing you do is draw your little pie chart or write the equations down. The same thing for the power pie chart, where and this is kind of called Watt's law, where the power or the rate at energy is being used is equal to the electromotive force times the current. And if you go through the algebra and substitute Ohm's law, you can get it in the other two forms where it's equal to the current squared times the resistance, or the voltage squared divided by the resistance. And we talked about coulombs before. So if you have 1 coulomb of charge at 1 volt potential, that's equal to 1 joule of energy. So that would also be equal to 1 farad when we talk about capacitors here a little bit later. So that's how much energy a 1 farad capacitor would be storing in its electrostatic field. And 1 watt, named after James Watt, who's this Scottish guy that invented the steam engine, and he did a lot of power stuff, is 1 joule per second. So that's the rate at which you're using the energy. And if you convert that, it's also equal to 1 ampere volt. And again, there may be a question. You might get a question where you have to actually plug in some numbers on the formula. If you remember the formula, it should be easy.
Yeah.
Okay, we talked about these prefixes and conversions. The ones you need to remember are giga, mega, and kilo for the positive ones. And the exception there is kilo, which we use a small k, and I can't explain why, because the other ones, mega and giga and Trying to think what the next one is. Bigger than a giga. Anyway, they're all capital letters. And when we get to the numbers less than 1, they're all lowercase. And kilo is the exception. And there's kind of a tricky question that you might get about that one. So that's
Okay.
one to remember. But kilo means 1,000 of something, or 10 to the third. Mega is 10 to the sixth, and giga is 10 to the ninth. A milli, like in a millimeter, would be 1,000th of a meter. A micro or a micrometer would be 1,000,000th of a meter. We have nanos. Usually we're talking about capacitors when we talk about nanofarads and picofarads, where a picofarad is 10 to the minus 12th and a nanofarad is 10 to the minus 9th. When we talk about inductors, we're usually talking in the millihenries or microhenries, possibly nanohenries. And the other ones that were part of that session was decibels. So you don't necessarily need to remember the formula, which is 10 times the base 10 log of some ratio. And when we talk about things like antennas, where we're using it as a reference, remember that 1 decibel relative to a dipole, which is the dBd, is equal to 2.15 decibels relative to the isotropic radiator. I put that on there because there is a question where that's the answer. Any questions on the conversions and how you move decimal points left or right?
Oh, no, I have no problem with that.
Pat?
Well, I understand it. I am not proficient.
Well, you can miss 9 questions and pass.
Okay.
I'm going to miss that 1 dB one. If
Miss
that
the
comes
what?
up, I won't say that. We're just going to keep on going. Keep driving. It's okay.
Okay, we talked about components. So first one was resistors. Like I said, they oppose current flow and they're not frequency dependent. So they don't care whether it's direct current or alternating current. There's a question about that. So that's something to remember. There are adjustable resistors, which got the name potentiometers because that's the way they were typically used. So you could vary a voltage with it, which is, so you were varying the potential. So that's how it got that name. You'll usually find it as a volume control on a radio or something, or a voltage adjustment knob, like on a power supply.
Or like a dimmer switch?
Or a dimmer switch, yeah. Now, in a lot of modern stuff, they don't use adjustable resistors anymore. You're actually turning an encoder. And
Doing
it's
what?
kind of like an encoder, which is gives you a digital count as it's rotated. So it's kind of a digital way of doing what the old adjustable resistor did.
Like on my toaster.
It's what?
I have a toaster and you set how much toasting you want with a knob and it shows a number.
Yeah.
As opposed to darker, lighter.
Yeah.
continuous?
It may, if it's a smart toaster, it may have a encoder in it as opposed to a potentiometer. Okay, we have capacitors. The main thing to remember is they store energy in an electric field. And we talked about how much energy was stored in a 1 farad capacitor. And remember, farad is named after Michael Faraday,
Right.
who did a lot of experimentation with that kind of stuff.
Mhm.
He wasn't much of a mathematician, but he kind of was a very good experimenter. Capacitors are essentially conductive surfaces separated by some insulator, or we call it a dielectric, which is kind of a fancy name for an insulator. Inductors, kind of the opposite, they store their energy in a magnetic field. And essentially, it's just a piece of wire wound into a coil.
Mhm.
So the magnetic fields around the wire interact when it's wound as a coil, so it increases the inductance of it, and also the magnetic field. We had batteries, which also store energy, but they do it typically in some form of electrolyte. And you can have rechargeable and non-rechargeable batteries. There's questions about those. Remember that a
Right.
lead zinc battery is rechargeable. A flashlight battery or carbon zinc is not. Lithium ions and nickel cadmium, and what's the other one they don't use much anymore? Anyway, those are rechargeable. I think the only non-rechargeable that shows up as an exam question is the carbon zinc battery. Okay, then we got into semiconductors, and we talked about diodes, which is the most basic semiconductor. It consists of a junction of a piece of P material and N material that can be made out of germanium or silicon. For some very high frequency stuff, they're also made out of some other materials like gallium arsenide, but those are more exotic things. Typically, it's going to be silicon. You'll still find germanium diodes, but I'd say 95% are going to be silicon. Because of that junction, there's a bias voltage that you have to overcome that's created by the junction itself. And in the case of germanium, that's approximately 0.3 volts. In the case of silicon, it's approximately 0.7 volts. So you have to apply, in the case of silicon, at least 0.7 volts across that diode before it will conduct.
Mm-hmm.
And that means a positive 0.7 volts on the anode with respect to the cathode. Typically, diodes, at least the small ones, are marked with a stripe around one end, which designates the cathode. Sometimes they're also kind of bullet shaped, where the kind of pointy end is the anode. As far as the exam question, it's the stripe on the cathode. There are special diodes. You learn a lot more about those in the general exam, but on the technician, the only one is really the light emitting diodes, which, in addition to acting as a diode, and conduct current when they're forward biased, they also emit light. And depending on the color of light, the amount of bias voltage varies. So instead of being 0.7 volts like silicon, they may be 2 volts or 3 volts. I think I've seen them up as high as maybe 4 volts. And because they use different material to get the different colors, and it requires different bias voltages. Next, we went into transistors, which is a diode junction with yet another piece of semiconductor. So we can have a sandwich then, which is a P material, N material, and P material, or N material, P material, and N material. We call those PNPs or NPNs. And the basic difference is it will conduct current like a diode, except the middle layer called the gate or the base, depending on whether it's a bipolar or field effect, will control the current flow. Wherein a diode, once you exceed the bias, it's going to conduct. In a transistor, the amount of current or voltage on the control element will control how much it conducts. That's why we can use a transistor as a switch to turn things on and off, or as an amplifier where we can proportionally control the current flow. There's two fundamental types of transistor. Bipolar junction transistor, which are kind of like the diode, is just a sandwich of those three pieces of semiconductor. And we call the electrodes that are attached the base, collector, and emitter. So the collector would be the most positive element, the emitter, the negative, and the base would be the center piece, which is the controlling element. In the case of bipolar, it's a current device. So the amount of current that's going into the base to the emitter controls the amount of current that flows between the collector and emitter. The other type is called a field effect, and it's more like a vacuum tube where it's controlled by a voltage instead of a current. And we label the elements different. They're gate, drain, and source, where in this case, because they were developed later, they're referring to electron movement. So the source of electrons would be equivalent to the emitter on a bipolar, and the drain would be equivalent to the collector. So the electrons enter the source electrode and come out the drain electrode. The one in the middle we call a gate because it kind of acts like a gate. Mm-hmm. And as you apply a positive or a negative voltage on the gate, depending on the type of field effect transistor, it will control the amount of current that flows between the source and the drain. So, any questions on those? I think if you remember the things we just talked about, you won't have any trouble with the questions. Mm-hmm. Okay, we also talked about schematics and schematic symbols.
Mhm.
You're probably guaranteed to get one of these where you'll have to identify a component on a schematic. And if you remember, the resistor was the jagged line.
Mhm.
A transistor, in that case, it's a bipolar transistor, and you can see the collector base and emitter electrodes. And in that case, you see the small arrow, which is pointing out to the emitter,
Mhm.
which is an NPN transistor. The next one over is a symbol for a lamp or an indicator, like the old pilot lights that you used to see in radios and things that lit up, kind of like a flashlight type bulb. It's still an exam question, but you don't see those much at all anymore. Next is the battery, and it's shown as a set of plates put together, because that's actually how Mr. Volta, who we named Volts after, developed the first battery, which he called like a voltage pile or something like that. Which was a stack of dissimilar elements that would actually generate a voltage across them. Next, we have the symbol for a transformer. You can see it's labeled primary and secondary, with those vertical lines showing that there's some sort of core material. It could be ferrite, it could be iron laminations, like for a power transformer. Just need to remember what the symbol looks like. The next symbol is for a diode, although they don't normally have that line going all the way through the little triangle.
Can I ask a question here? So
Sure.
in your horizontal list of components, is that the order of the symbols? Or am I not that lucky?
No, it is.
Okay, so this one with the A and the arrow and
The C.
that,
Yeah,
that's
for
a
the cat.
transformer? The transformer?
No, that's the rectifier.
Yeah. But
Right, rectifier. But you said diode, so is a rectifier a diode? Did I miss that?
Rectifiers and diodes are the same thing.
Thank you. Okay, never mind.
When we use it as a rectifier, we call it a rectifier. It's still a diode.
Okay.
It's an old name that been around a long time, and they still use it. It's still a diode. Now, typically, rectifier diodes tend to be made to handle a lot more power, so they may be a little bit different than a small signal diode, but the symbol is still the same.
Okay.
Next one is a capacitor, just a plain old ordinary capacitor. Sometimes you may see one of those plates as a curved line instead of a straight line. It really makes no difference. Same thing. You notice it says non-polarized. If it was an electrolytic capacitor, it would have a plus and minus on it, because they are polarized and they don't work for alternating current. They're used as essentially DC filtering devices to store direct current. Next, we have a special diode, the LED. Okay, still the diode symbol, but you see the little light rays coming out to indicate that it emits light. We go down to the next line and we have our variable resistor, which is just shown with the arrow through it, showing that it's adjustable. Next is sometimes how we represent a potentiometer. So it has 3 terminals. Sometimes it appears that way, or the little arrow part may be connected to something else instead of down here. To the right is a variable inductor. I don't think that's one of the exam questions, but just remember it. And then lastly, we have the symbol for an antenna. So the other things to remember are that transistors control the flow of current. So whether it's a bipolar or a field effect, even though you control them with current or voltage, they both control the flow of current through them. We have physical switches, which don't have a symbol there. There may be a question about a single pole, single throw switch, which we use the SPST as a shorthand for it, where it will open and close a circuit. You could also have a single pole double throw, which means it can connect between 2 different circuits. So when it opens one, it connects to the other one. I think the other thing to remember on diodes, because I believe there's a question like this, is it converts AC into pulsing DC. And that's really when it's used as a rectifier. And transformers will convert alternating current into another voltage that's dependent on the turns ratio between the primary and the secondary. So if the secondary has more turns of wire on it than the primary, you will get a higher voltage out of the secondary. Likewise, if it has less, you'll get a lower voltage.
So I'd like to interject some recent experience that I had. And it's just a story. But so the chargers that we have that have that box on it with little bitty electrical words on it, they come with, your computer and whatever. So
Yeah.
I was clearing out stuff in my garage going back probably 30 years that I've been throwing wires and chargers and telephones, whatever, into these boxes. And it was time to say no more of that. So I went through them all and I made a nice big cardboard box of them all. And then I thought, I wonder about these charger things. I mean, what of these things should I not be just throwing in the trash? So I asked a friend of mine, he's a software guy, but I thought he might know. And he said he thought they were power supplies, but I was a little doubtful about that. So I asked my AI program. I was lucky enough to pick up one of them and said, oh, I'm an adapter. It said right on it, I'm an adapter. So then I was able to ask my AI program, could I recycle an adapter and what it was? And it explained to me what it was, which was right in this neighborhood, right? It said it converts alternating current to direct current in that case, which is what a lot of electrical components like in your computer want. And no, don't put it in the trash. You have to do special recycling. That's my story. That we managed to use these things for 30 or 40 years without knowing even what they're called.
Yeah.
Well, sometimes they call them wall warts.
Wall warts.
Yes. That's cute.
It's a
I wonder if that would work. I'll have to ask my AI program if it knows what a wall wart is.
It's essentially,
Probably not.
it's essentially a little transformer
Yeah.
with a rectifier and maybe a filter capacitor, and possibly a Zener diode as a regulator. So they'll put out, 5 volts, 9 volts, 12 volts. If you get one for, say, a laptop, it's probably more like 18 or 19 volts.
Mhm.
But yeah, they're all fundamentally the same thing. Some of the newer ones might actually have a small switching supply,
I have some of those.
and those tend to make a lot of RF noise.
Mhm.
Ah,
Yeah, I've got one that goes from like 3 to 12. They have different heads to change them out as power supplies.
ah,
And they're very convenient to have in an emergency, like you just need something.
yeah.
But because I don't use them that often, but occasionally it's like, well, do you have this? I have a 5 volt. Yes. I have this little thingy. It converts it. Yes. We just have to find the right port because they have the different, and then you have to put it on right, positive to negative. So if you don't have it on right, it won't work. So you switch it around. Oh, voila, it works.
Okay. Any other questions?
More stories. No more stories.
Okay. Okay, so we also talked about resonant circuits. Essentially, two types can be a series circuit or a parallel circuit. If it's series, it means there's an inductor and a capacitor connected in series, and it will have a very low impedance at resonance. In other words, that's the frequency at which the inductive and capacitive reactances are equal and cancel out. If it's a parallel circuit where you have the inductor and capacitor connected in parallel, it's going to be just the opposite. It will have a very high impedance when it's at the resonant frequency. If you apply a DC voltage to either of these, in the case of the series resonant circuit, it's going to appear as a very high impedance, essentially an open circuit, because the DC is not going to travel through that series capacitor. If you apply a DC voltage across the parallel resonant circuit, sometimes we call them tank circuits, it's going to appear as a very low, because of the inductor, it's almost going to look like a short circuit, just a straight piece of wire. So that's the main thing to remember, is they behave just the opposite when they're at the resonant frequency as they do when they're at DC. We talked about switches. I mentioned the single pole double throw, where it allows you to make a connection between two different circuits. I'm pretty sure there's a question about that. We talked about relays, which are just electrically controlled mechanical switches. Nowadays, you also have solid state switches, which are electrically controlled electronic switches. But I don't recall there's a question on those yet. However, the question pool is due to change next July. So there'll be a whole nother set of questions next year.
Okay.
We talked about meters, which are used to display a numeric value of some quantity, whether it's a voltage or a current or S units or VU units on a stereo or some such thing. can be either analog or digital. We talked about integrated circuits. The main thing to remember is just multiple either analog or digital devices in a single package. So they just put a whole bunch of things in this little integrated circuit with a bunch of leads coming out of it. We talked about regulators, which are used to maintain a constant voltage from some higher voltage source. So the wall wart we were talking about has some form of regulator in it, because you're going from 120 volts AC down to some pulsing DC that you then regulate out to your 5 volts or 9 or whatever it's set for. We talked about fuses, which are there to protect the other components from excessive current. So you want the fuse to be set at a value that's just slightly above the maximum current the device is rated for. And it's really there to prevent damage and fire, possibly fire. If you didn't have the fuse and you had an overcurrent, like a short in it, it could get hot enough to cause a fire. We mentioned shielded cable that is making use of what's called a Faraday shield, which is a conductor around the wires to prevent coupling of unwanted signals or also radiation from the wires themselves. So it prevents external fields from affecting what's inside the shield. Okay. We talked about radio waves, which are electromagnetic waves. It's just part of the spectrum. Electromagnetic waves are anything from above DC to infinity. It includes visible light, ultraviolet, infrared, X-rays, gamma rays. They're all electromagnetic waves, and they all consist of an electric and a magnetic field, which are orthogonal to one another. It means they're at right angles. So if you familiar with the right-hand rule that you use for like screws and things, you can do that with electricity. So if you assume you have a wire running through the palm of your hand, your thumb would be pointing in the direction of the electric field along the wire, and your fingers would be representing the magnetic field, which is perpendicular to it.
Oh, that's a great way to remember.
We talked about wavelength and the speed of light. You need to remember that the speed of light is approximately 300 million meters per second in free space. And the wavelength is how far a wave travels in one cycle. In other words, going from 0, positive, 0, negative, back to 0. And that's where we use this little shorthand formula of 300 divided by the frequency in megahertz. So that way we get rid of that, those 6 extra zeros.
Yeah.
And obviously the wavelength is going to decrease as the frequency increases because you're dividing 300 by larger numbers. Therefore, the wavelength gets smaller and smaller. Um, I mentioned or didn't mention the upside down Y, which is a lambda, Greek lambda symbol, which we use to represent wavelength. We also refer to wavelength for the different amateur radio bands. Instead of talking about specific frequencies, like 3 to 30 for HF and 30 to 300 VHF, 300 to 3000 for UHF, and all those go up by factors of 10. So there's an LF, which would be 0.3 to 3 megahertz. And then there's a super HF, which would be 3,000 to 30,000. And the term of RF, it really is referring to any frequency. There's nothing special about RF. It can be any of those. You will hear amateurs talk about, say, the 20-meter band, which instead of being 14 something megahertz, they'll just use 20 meters. And if you divide 20 meters into 300, you'll get 14 something. So that's just kind of a shorthand that you need to get familiar with. And the amateur bands go from, well, I think now there's even a 640, maybe even a lower one, kilohertz, or meter, excuse me. Typically 160 meters, 80 meters, 40 meters, 30 meters, 20 meters, 17 meters, 15 meters, 12 meters, 10 meters, 6 meters, 2 meters, and then you get into centimeters. Any questions on meters? Just remember the 300 million meters per second. When we talk VHF or UHF communications, question? Basically, we're talking about line of sight communications. At those frequencies, you don't normally get much propagation off the ionosphere. So in the case of having a technician license, you'll mostly be operating VHF and UHF, either with a handy-talkie or a base station. So you're limited to line of sight as far as direct communications, or what we call simplex, where the distance you can get is due to the sum of the distance to the horizon of each of the people trying to communicate. And there's a formula for calculating the horizon distance, and it's 1.23 times the square root of the height in feet. So if you're a very short person, well, no, let's say you're a very tall person, and your radio in your hand is at 9 feet above the ground. It means that the distance to the horizon for you would be 3 times 1.23, or in other words, 3.6 miles. Now, if you had another 9-foot person on the other side of the horizon, they'd be at another 3.6 miles, so you could do a 7-mile communications. Now, it turns out that there actually is some refraction, because radio waves, when they're traveling along the surface of the Earth, even in VHF and UHF, tend to curve along the surface a little bit. So you actually get a little farther, about 15%. So you use 1.414 instead of the 1.23, and that's what we call the radio horizon. So it means the signal is going slightly beyond the visual horizon. I don't know that you have the formula. Yes?
So I'm looking at the line of sight, and I thought I was following along. And it says a capital D equals D1 plus D2.
Right.
So just remind me what D1 and D2 are.
Yeah.
Two different people,
Different people.
or, well,
So small
radios.
d really is a person. So P1, oh, to calculate D1 by calculating the height of person 1 times
Yeah, just think,
1.23, unless we like 1.414 instead. Okay,
right.
I'm good.
Assume D1 is a transmitter and D2 is a receiver.
Yeah, well, the first line says line of sight equals capital D equals, that's the one that threw me once we went a little further. So we calculate the line of sight for one guy, and we calculate the other line of sight for the other person. You add them together, and that's the actual line of sight.
Right. That's the maximum distance they should be able to communicate.
You can see my problem because it says two different things for line of sight. Just saying.
Of course, there's exceptions to that because we've proven it where we've done simplex communications between Merritt Island and Vieira, which is a lot farther than the formula says. Okay, when you're doing these kind of line of sight things, you can get what's called multipath because the signals can be reflected off of buildings and things.
Mm-hmm.
So it can arrive between the transmitter and receiver by different paths. And of course, one path may be longer than the other. So they'll get there at different times, and they can either wind up being in phase or out of phase. If they're in phase, the signals would add together and be stronger.
Mm-hmm.
If they're out of phase, they subtract from one another, so it'd be a weaker signal. If you happen to be moving, like in a car, I guess if you had your handy-talkie and you were out on your morning jog, you could also get the picket fencing because of the change in the paths as you move. You can get the adding and subtracting, which is causing this flutter, which when you hear it in a car moving fast, it's kind of sounds like, kid on the bicycle, dragging a stick along the picket fence as he goes by.
Oh,
That's kind of where that term came from. And the signal will be in and out, in and out, in and out. If you're trying to do data like digital voice, and you're getting these effects, you get some very high error rates, and digital voice doesn't work very good. Digital voice is very clear until it's not.
Yeah.
In the case of analog, I mean, you can even kind of hear it down in all the noise and everything going on. That's not the case with digital. Digital is digital. It's either there or it's not there. These buildings or other things that signals reflect off can also be used to your advantage, where you might be able to get around an obstacle by reflecting your signal off of something to get to the point you want to get to. Kind of theoretical, but yeah, you can do it. There's also a thing called knife edge diffraction, which I first learned about making telescopes, and light waves as well as radio waves tend to bend or refract around a sharp edge. So it could be the edge of a building, or they even claim like the top of a mountain. I never considered those that sharp, but that's what it says in the textbooks. So those can actually bend radio waves just like they do light waves, because they're all electromagnetic waves. Another issue when you're talking about VHF and particularly UHF communications is that those signals can be absorbed by water or things that contain water, like rain, fog, trees, people. People are mostly water, which is why in these big convention centers, they have to have a lot of access points because of the signal being absorbed by all those people. We also have to consider polarization of the signal. And if you recall, we defined polarization as the orientation of the electric field relative to the surface of the Earth. So if you have your antenna, say your handy-talkie, and you turn it sideways, then the electric field that it's producing is going to be horizontal relative to the Earth. If you hold it upright, it's going to be vertical. So when you're talking straight line of sight type communications, the polarization makes a big difference. I mean, if you're familiar with polarized lenses, if you take two Polaroid filters and you rotate them, it can block the light out.
Mm-hmm.
You have the same effect. If you're transmitting vertical and the person you're trying to talk to is horizontal, you're hardly going to pick up any signal. So both ends need to be the same polarization. Now, that's not true when we talk about HF communications, where we're using refraction off the ionosphere because it gets converted to a circular or elliptical. That's a whole different thing we hadn't got to. And we've mostly talked about just straight line of sight between two, say, handy-talkies, but you have the same issue when you're talking to a repeater. And most repeaters, I don't know of any that aren't, in the VHF, UHF, are going to have a vertical antenna, so they'll be vertically polarized. So if you're trying to talk to a repeater, you need to hold your handy-talkie straight up. Okay, there are some propagation modes that you can find in the VHF range. There's one called sporadic E, where you can get some, it's not exactly refraction, you get reflections off of particles in the E layer of the atmosphere. And that can happen on the 10, 6, and 2 meter bands. So it allows you to do some possibly over the horizon communications. But the reason they call it sporadic E is it's a very sporadic communications, because you're relying on signals bouncing off of ionized particles in the E layer of the ionosphere. You can have the same type of thing with auroras. So off of the northern or southern aurora, you can get backscatter, which is the same kind of thing. You're getting waves that are being reflected off of ionized particles. In the case of the auroras, it's a very distorted, varying signal because they're not at all steady. If you've ever seen pictures of them, they kind of dance around.
Mm.
It's also possible to have signals bounced off of meteor trails. When a meteor enters the atmosphere, because of its velocity, it creates enough heat to ionize the atmosphere, and it leaves a trail of ions behind it. And you can bounce signals, they tell me, off of those meteor trails, and they may last from 30 seconds to 2 minutes. Doesn't give you a whole lot of time to make some kind of contact, but people apparently can do it.
They like a challenge.
Yeah. There's a thing called tropospheric ducting, or in the troposphere, the lower part of the atmosphere, you can have an inversion layer where you have a warm layer rise above a colder layer. And that kind of forms this little tunnel, which we call a duct. And you can actually have signals bounce their way through that duct and go for some very long distances. I can't say I've ever tried it or experienced it. And also we talked about absorption, precipitation, fog, rain, that kind of stuff affects mostly UHF and above. There's really no noticeable effect when you get below 30 megahertz. So down in the HF band, it's not a problem. There's a question to that effect, which is why that's on there. Okay. Some of the other propagation modes, when we're in the HF and some of the VHF frequencies, you can get refraction off the ionosphere. When you're down in the HF band, when you're getting refraction off of the F1 and F2 layers, you can get halfway around the world, and actually, in some cases, you can go all the way around back to yourself and hear your echo. So you can get very long distances down in the HF frequencies. You may get something called fading because those refractions are taking possibly different paths, and they don't all get to the receiver at the same time, like the multipath we talked about earlier. You can have that same sort of effect because the surface of these layers in the ionosphere is not smooth, and it is moving and varying. So you can get this fading effect because of that. The ionosphere ionization is proportional to the sunspot cycle because that's what creates the radiation that ionizes the ionosphere. So the greater the sunspot cycle, the greater the ionization of the ionosphere, and the longer distance you can get in the 6 and 10 meter bands. And in the 10 meter band, which is a technician, you can operate on phone in a sub part of that band. And between dawn and a little bit after sunset, it opens up pretty good. And here a while back, it was really good. It varies depending on the current sunspot cycle. As I mentioned before on polarization, when we're talking about signals that are refracted off the ionosphere, there's this magic that happens, and it converts them into an elliptically polarized signal as opposed to being horizontal or vertical. So it doesn't really matter when you're transmitting or receiving, in that case, whether you're using horizontal or vertical. For things like beam antennas and stuff, it's typically easier to build them horizontally than vertical, but it doesn't really matter. So in order to do any of this, you need an antenna. One of the simplest one is the horizontal dipole, which, because it's a horizontal wire stretched parallel to the earth, is horizontally polarized. So you get this radiation pattern that's broadside to the wire. In other words, if your wire was running north to south, your radiation is going to be east and west. And when you're doing an antenna, you also have to bring in what we call the velocity factor. If you remember, we said the speed of light was 300 million meters per second in free space. When a wave, electromagnetic wave, is moving through a conductor, it doesn't move at 300 million meters per second. In like a copper wire, it's typically 95% of that. So that's where that 0.95 velocity factor comes in. So if we try to figure out how long a wire we need for a half wave dipole, we divide the wavelength by 2 and multiply it by 39.4 inches per meter, and then apply the velocity factor to find out how long a wire you need to make that half wave antenna. Of course, when you do that, you better add some extra length, because even though your calculations might be down to 4 decimal points, because other things affect it, your answer is not going to be right. So if you're not resonant where you think you're supposed to be, then you have to adjust the length of the wire. So if you need to raise the frequency, you need to shorten the wire. If you need to lower the frequency, you need to lengthen the wire, which is why you add some extra wire, and then you just fold it back upon itself as you adjust the length. Because if you cut it off and you need to make it longer, you may have to attach another piece of wire to it. It's better to have some extra length to start with. The other basic antenna is called a quarter wave vertical. It's essentially half of a half wave dipole mounted vertically, and the ground itself is acting as the other element in that half wave dipole. And the radiation pattern around the vertical is going to be like a donut. They call it a toroid or torus. So it's omnidirectional around the vertical antenna, which is one advantage. It does give you omnidirectional transmission and reception, but at a lower gain. Typically, a half wave dipole will have about 3 dB more gain than a vertical antenna. But it's limited to radiation broadside to the wire. And it's kind of hard to move a horizontal dipole around at lower frequencies. Now, if you get up to VHF and UHF, it's no problem because they're very small. The other thing is called antenna loading, which you see this in mobile installations where you can't really have a 10-foot antenna on the back of your car. I mean, I guess you can, but it's going to hit stuff. So one way to make the antenna shorter is to electrically lengthen it. So you add an inductor, we call that a loading coil. So it allows you to make the length of your antenna much shorter, but it's a compromised antenna. And actually, the only part that radiates is the vertical section, not the inductor itself. So you lose gain on the antenna when you do that, at the expense of having a very long antenna sticking up on your vehicle. We talked about the half-wave dipole, which is somewhat directional. In other words, it's broadside in two directions. You can have an antenna that concentrates all of its signal in one direction. We typically call those beam antennas. And they have increased gain, although there's no power gain. But because the signal is directed in one direction, you have a higher radiation pattern in that direction. So if you're putting 100 watts into that antenna, say it was a vertical, then that 100 watts is spread around in that donut. So the surface of that donut is going to be your 100 watts divided by whatever that surface area is. So the larger that surface, the smaller the watts per square centimeter. When you change that pattern into a very narrow lobe in one direction, that 100 watts is spread over a smaller area, so the watts per square centimeter is much higher. It's still only 100 watts. Probably the most common beam antenna is called a Yagi. Technically, it's a Yagi-Uda, which is named for Dr. Yagi and Dr. Uda, who invented it. I actually think, from what I've read, Dr. Uda did all the work, and he worked for Dr. Yagi. Sometimes you're going to have a very inefficient antenna. We call those rubber duckies, which you find on your commercial handheld handy-talkie. The little stubby, 6 or 8 inch rubber thing sticking up, which has a loading coil in it to make it that short. So it's a very inefficient antenna, but it's done that way so it's hard to break it. You can get replacement antenna, a whip that's 18, 19 inches long, which gets it closer to a quarter wave for UHF, which works a lot better, but it's a little bit of a pain with that long whip sticking up. If you're trying to use your handy-talkie in a car, you're going to be affected by essentially a Faraday shield of the car itself, unless you're in a Corvette or a Jeep that's mostly fiberglass top. If it's a metal topped car, you need to kind of hold it out the window or close to the window to get much reception. Also, there's mobile antennas that are 5/8 wavelength as opposed to quarter wavelength. And it actually has up to 2 to 3 more dB of gain than the quarter wave. You don't have to understand why, just that's a fact, and there's a question about it having more gain. Okay, in order to connect to your antenna, you need what we call a feed line. And feed line is typically going to be made of, excuse me? Your feed line is typically going to be made out of coax. Normally in amateur communications, it's going to be a 50 ohm coax, which is the most common. You'll see 75 ohm for like cable TV or maybe broadband. Almost all amateur radios operate on 50 ohms. So your radio is going to be 50 ohms, your feed line is going to be 50 ohms, and then you're going to need some matching network because your antenna is probably not 50 ohms. And we talked about in the impedance of the coax, the impedance is the opposition to alternating current flow, or RF current. We also measured in ohms, and the impedance, the coax has what they call a characteristic impedance. So in most cases, it's 50 ohms or very close, 50.1 sometimes you see. And that's measured by if you were looking into that feed line, the impedance you would see if it was infinitely long. So in the case of what we use, if it was an infinitely long piece, didn't matter what was on the other end, it would appear to be 50 ohms. If you try to calculate what it is, it's very complicated because it's a lot of series and parallel inductance and capacitances stuff. Basically, you just remember it's most commonly 50 ohms impedance. There are losses associated with the coax. It's not perfect. And the higher the frequency, the more the loss. So essentially larger diameter coax, and also depending on the type of dielectric or insulation that's in it, will have less loss than smaller ones. So when we say RG213, that's a nomenclature for kind of a standard half-inch diameter 50 ohm coax. RG58 is a quarter-inch 50 ohm coax. So the half-inch will have much less loss than the quarter-inch. And they measured in loss per 100 feet in decibels. If you want to have the lowest loss up at the high frequencies, and that's usually how you connect the repeater to a repeater antenna, you use what's called hardline, which is like copper tubing with a center conductor that may be separated with a little spiral insulator, so it's essentially air as the dielectric, or it could have some foam. The downside of hardline is it's not only expensive, hard to work with, it does require special tools to put connectors on it. Regardless of whether it's hardline or coax, you can have a problem with water intrusion where it can get into braid and cause the braid to corrode and disintegrate, or actually get into the foam insulation. Can give you some very high SWR readings, and is normally caused by ultraviolet damage to the outer sheath on the coax. So if it's coax, it's going to be used outside. You need to make sure that you get UV rated coax. They also sell some that are rated for direct burial, where you can put it in the ground. And those have a much tougher outer coating to prevent water intrusion. Any questions on coax?
No.
You need to deal with connectors. So you'll have a connector at your radio to your feed line, and between your feed line and your antenna, maybe more along the way. The most commonly used connector in amateur radio is called a PL259, which is the male portion of the connector. The female end is called an SO239. And they're used at HF and VHF frequencies. There's also a type N connector, which costs 2 or 3 times as much. It works much better at higher frequencies, particularly UHF. And because of the way it's made, it's more water resistant. I won't say it's waterproof, but it's more water resistant. We mentioned SWR, which is a way we measure how well the transmission line is matched to the antenna or the load. So if you had a perfect match, meaning your radio was 50 ohms, your transmission line was 50 ohms, and your antenna was 50 ohms, in theory, you'd have an SWR of 1:1, which would be a perfect match. If you have an SWR of below 3:1, you can normally operate okay. 2:1 is usually pretty good, and you don't have that much loss due to SWR. When you get above 3:1, most modern transistorized transceivers will start to cut back on the output power in order to not damage the output power transistors. And I have seen that because I had a not exactly a lightning strike, but I guess close enough that it triggered the gas discharge tube in one of my antenna switches, which caused it to be a short. And I was still able to send power into the antenna switch, even though it was way down to maybe 20 watts or so. Wasn't going anywhere.
Mm-hmm.
So when you have a very high SWR, it's not only just a bad match, but because part of the signal is being reflected back, and then part of that may be reflected back again, every time that signal traverses the feed line, due to the loss in the feed line, you're going to have some loss of that signal, which creates some heating. So if it's a very high SWR, you may have that thing reflecting back and forth a number of times until it's totally dissipated, which can cause excessive heating in the transmission line. Just like you were trying to run 1500 watts into a RG58, which isn't rated for that kind of power, and it would overheat and damage the transmission line. You can have a similar thing trying to operate at very high SWR levels. So we talked SWR. How do you measure SWR? Well, obviously there's a thing called an SWR meter. A lot of your modern radios will have that feature and display the SWR that they're seeing going into the feed line. And in some cases, they may have a built-in, what they still call a tuner. It doesn't tune anything, but it will try to match the 50 ohm impedance of the output of your radio to whatever impedance it's seeing on the feed line. So even though you have a 50 ohm feed line, if the antenna, or say 200 ohms, you're going to see more like 200 ohms on the radio end of that feed line. So that's what that tuner function does, is try to make a impedance match between the radio and what it's seeing on the feed line. Normally, you would try to have that sort of matching device up at the antenna so that your feed line, when it connects to the antenna, thinks it's talking to a 50 ohm antenna, regardless of what it is. One of the other things that is useful in doing these measurements is a dummy load, which is a non-inductive 50 ohm resistor, usually in a box mounted on a fairly large heat sink, so that it can dissipate the heat for a while. They're all limited to how many watts you can put into it for a specific amount of time. I have a little 300 watt one that will do 300 watts for, what does it say? 300 watts for 30 seconds. But it will do 20 watts for 6 minutes. So the main thing is in the dummy load, which you can use for testing, so you don't have to transmit on the air. You just connect up to your dummy load instead of the antenna. And then you can test your setup and make sure everything seems to be working correctly into the dummy load.
Hey, Bob, it's time for me
Yes?
to go. So I'll be signing off here, but I just want to thank you very much for this class, and
Okay.
and remind you to send me Gary's email address so I can go ahead and embarrass myself. No, I'm going to. Yes, never mind. Thank you very much. I really appreciate your time and
You
knowledge.
might surprise yourself. The test is not that hard.
Yeah, well, people say that when they know stuff, but still.
I'm just going to keep reading these over and over before so that I'm ready, because I can't even get it. Still can't get into the site to get the FRN.
It's
Yeah,
like understanding it and without any experience at all is kind of tougher, but I'll give it a shot since you recommend it. And I mean, there's nothing bad will happen
Yeah,
if
well, I'll
embarrass
see you
myself.
there on Saturday.
Okay. All right, good. Thank you
Al-
again.
Although I
Bye.
can't give you a break.
Pardon me?
I said I can't give you a break. I have to grade it like I don't know you.
Oh, of course. And you shake your head and you'll say, we talked about that for a half an hour. What's your problem?
Oh, I I did talk to Gary about the FRN, and assuming that this doesn't get resolved before next Saturday,
Mm-hmm.
uh, how they were going to handle it, and he was going to look into it.
Okay. Well, I
So
can't do anything next Saturday because I'm going to be in, hopefully, it's still on Indianapolis.
Well,
I got to go to a rabbit show with my granddaughter.
oh, how neat. But I hope you make it. I hope you do.
Well, right now, everything I'm seeing is just major delays at OIA, which, we're always there 3 hours ahead because 2 hours never works.
Oh, dear.
Yeah. So we'll be sitting in airports Saturday and Monday.
well, anyway, I think you'll still be able to take the exam even if they don't have it resolved.
Okay.
And have to worry about it later, because if
And you
they don't
said I
have it
could take it online
resolved,
if I can't find a place to take it locally or, within a reasonable
oh yeah,
driving distance. Okay.
yeah, you can find online ones.
Okay.
But if you can't get the FRN, they probably can't
Oh,
process the
that's true.
application anyway.
Gotcha.
So you just have to take the tests and wait until things get resolved.
Yeah, that's true.
All right.
Okay.
I'll see you next Saturday, Pat. Oh,
No, she's
I
gone
guess
already.
she left.
Yeah.
Okay. Let's see. Oh, the different ways of measuring. There are SWR meters, both analog and digital, that will, in some cases, I think most of them I've seen, will show you your SWR and forward and reflected power. Usually the analog ones are what we call a cross needle. And there's actually two analog meters.
Mm-hmm.
One is showing forward power and one is showing reflected power. And where those two cross, there's some scale behind it, and that'll show you what the SWR is. In the case of digital ones, they just have digital readouts for all three. You can also use a directional watt meter. Kind of the industry standard is a Bird watt meter. And they measure forward power and reflected power, but not at the same time. You have it in forward mode and take a measurement, and you switch it to reflected mode and take a measurement. And then with those two, you can calculate what the SWR is. So regardless of which one you're using, you need to put it between the transmitter and your feed line to the antenna. And if your transmitter has a tuner in it, it may be showing you a SWR 1-to-1, but your external SWR meter might be showing a much higher number. You can also use what we call an antenna analyzer. Probably the most popular one of those is what is it? Rig Expert, I think, made in Ukraine. They're a little pricey. You can also use a Nano VNA, which are typically under $100. The Rig Experts are $500 and $600. MFJ used to make some. I don't know if they're still available in the $200-300 range. And like I mentioned before, the antenna tuners, whether they're in your transmitter or an external tuner, it's just a matching device. They don't tune anything. I'm not sure where the tuning actually came from, but it still hangs around. And
How
we
about
talked
an
about
adjuster?
loads. Okay, repeaters. If you're trying to do any distance in the FM, VHF, UHF, you'll need to talk to a repeater to get more than a few miles. Almost all repeaters are going to be FM, or in a few cases, phase modulation. I'm not sure. Basically, on a repeater, you're only going to hear one signal at a time, even though you might have two people talking on the same frequency. Because of something called the capture effect in frequency modulation, only the strongest signal is the one you're going to hear. So that's just a way that FM receiver circuitry works because of the nature of the signal. If you're doing single sideband in those upper bands, VHF and UHF, it's like I had mentioned earlier, it's just a special case of amplitude modulation where you're only transmitting one of the sidebands of the signal. So there's no carrier and there's no opposite sideband. Whereas in typical AM, you'll have a carrier, and on each side of it is the sideband, which is your voice modulation just shifted up in frequency. And it has a mirror image on the lower side. There's a convention that in the HF bands, because of the way equipment was designed and worked back a long time ago, that you use upper sideband if you were above 10 megahertz and lower sideband below 10 megahertz. It's not a regulation, it's just kind of a convention. And there are some exceptions, like one of them is in digital modes like FT8. It doesn't matter what frequency you're using, it's always going to be upper sideband data. And single sideband is used because it has a much narrower bandwidth than FM. Our single sideband is about 2.8 or 3 kilohertz. Most of your FM voice is going to be in the 10 to 15 kilohertz range. So you use a much smaller portion of the spectrum, so you have more power per hertz in that bandwidth. There's also fast scan color TV, which a lot of amateurs use, which is also another form of amplitude modulation. It used to be called NTSC, based on the National Television Standards Committee, and it used a 6 megahertz bandwidth for the TV image. They also used for broadcast FM for the sound. So old broadcast TV had very good audio. Continuous wave or Morse code, which is sometimes called, is also another form of amplitude modulation with a very narrow bandwidth of 150 it says it should be 150 hertz. And in CW, you're just turning the carrier on and off. Most people now will use an electronic keyer as opposed to just a straight manual key to send code, because it will automatically generate the dots and dashes for you. You just have to learn how long to hold the left or right key. So it sends much more readable code. We talked some about satellite operations. As a technician, you can talk to any of the satellites. You can listen to military satellites, maybe. You can listen and talk to any amateur satellite as well as the International Space Station. Most satellites have what we call a beacon, where they send down telemetry with health and status information of the satellite.
Mm-hmm.
In most cases, it's set as Morse code at like 18 words a minute. Because satellites are usually either solar powered or some other limited power supply. They do have limited broadcast power. So if you send a very strong signal to the satellite, it's going to try to rebroadcast that signal through its transponder at a high power, which means it's going to take power away from other signals that it might be receiving. So it's recommended that you don't try to use any more power than necessary when you're talking to a satellite. And there are some questions about how you determine that. And one way is the reverse function on the satellite, where you can actually listen on the input frequency of the satellite. And also you can compare your signal downlink with that of the beacon. And you should be about the same power level as the beacon. There may also be some other telemetry links on the satellite, which you can receive.
Mm-hmm.
There are tracking programs that work on computers. I suspect, I haven't tried it, there's some that you can do on a cell phone, which will show you sort of the real-time position of various satellites, what their apparent frequency is, because it'll take into account the Doppler shift. If you remember, Doppler shift is the apparent change in frequency of a source that's moving either towards you or away from you. So as it moving towards you, the frequency appears to increase. As it moves away from you, it appears to decrease.
Mm-hmm.
The tracking programs are all based on input data of what we call the Keplerian elements, which are things that are published with all the information about the various satellites that these programs can use to predict the positions. They're not actually getting data from the satellite. They're calculating where it's supposed to be based on those Keplerian elements, which show like apogee and perigee and various times and all that kind of stuff, the Dopplers. When you're talking to a satellite, they, in most cases, will support single sideband, FM, CW, and data. They will operate in what we call either a UV mode or a VU mode, which specifies the uplink downlink mode. So if it's in UV mode, it means it's receiving on UHF and transmitting on VHF.
Right.
If it was VU mode, it'd be receiving on VHF and transmitting on UHF. And remember, in a satellite, it's similar to a repeater, but in a repeater, there's a frequency offset which is in the same band. It's either 600 kilohertz if it's VHF or 5 megahertz if it's UHF. In the case of a satellite, if it's receiving on UHF, it's going to transmit on the VHF band, entirely different band, not just a frequency offset. And the satellites use transponders, which work a little different than a repeater. It just shifts the frequency of the signal it receives, as opposed to retransmitting it like a repeater. Satellites have this thing called spin fading because satellites rotate due to trying to maintain a constant temperature. We always called it rotisserie mode. And because they're rotating, the antennas rotate. So you're getting rotating polarization. So you will see the signal fade in and out because of that. People that really do a lot of satellite work will use crossed antennas where there's one set up on the same boom. One will be vertical and one will be horizontal, so it can compensate as the satellite rotates. We also have what we call LEO satellites, which means they're in low Earth orbit, and they're obviously very low. They have a very fast orbit time. I think less than like 99 minutes.
Wow.
Okay. Digital modes, you can operate in a lot of these newer digital modes. FT8 is probably the most popular one. There's actually a suite of software called the WSJTX, which has 8 or 10 different types of modes supported in it. FT8, FT4, JS8. There's MSK 144, which is one of them that's used when we talked about meteor scatter. There's one called Echo, which is used for people that want to do moon bounce and bounce the signal off of the moon. A whole bunch of things. One of the digital modes, an older one, is called packet radio, where you send a packet of data that has a checksum in it, a header, an automatic repeat request, which we call an ARQ, which is an error correction technique. So when they receive the packet, if the checksum doesn't agree, if the receiver's calculated checksum doesn't agree with what was transmitted, then it sends an ARQ to tell the transmitter to resend the packet. And it can do that several times before it gives up. There's another form called APRS, which stands for the Automatic Packet Reporting System, where systems can transmit using that protocol, and they can send GPS position and data, maybe some other text along with it, so you can track where these transmitters are. So they're typically mobile things, could be boats, cars. We do it in the 10-mile run at the Space Force Base, and have the lead and trailing cars doing APRS, and in some years we've had runners with the radio that had APRS, and you could track them real time. There's also another mode called PSK31, which stands for phase shift keying, 31 baud, which is a popular mode where it, instead of changing the frequency to represent different symbols, like something like FT8 does, it changes the phase. Some of the digital voice communication modes that I'll talk about is DMR, which stands for Digital Mobile Radio. The main difference between that and some of the others is it time multiplexes two different voice signals on a single channel, excuse me. I guess I need some water. That's the main difference. I haven't actually experienced anybody doing two voice signals at the same time, but it has that capability. They have a thing called talk groups in the case of DMR. In the other modes like D-Star and Fusion, they call them reflectors. Same kind of thing, where it's a kind of a private channel that's set up, which allows people to join that particular talk group and communicate with each other, and people that aren't connected or joined to that talk group aren't privy to the conversation. Whereas on a standard repeater, anybody that can receive the repeater hears what's going on.
Gotcha.
So that's mainly the difference in the talk groups and or reflectors. I mentioned the WSJTX software that supports all those different modes of digital things, which are all done via computer. Ooh, got a misspelling on Earth. There's also mesh networks, which have been popping up in recent years, where amateurs can take a kind of a commercial Wi-Fi router and load different firmware on it and set up a bunch of them in a network where they can find one another and make connections and form this kind of mesh, so that you wind up having some fault tolerance. There'll be a path between point A and point B through different routes. So if one of the nodes in that mesh fails, there's another way to get from point A to point B. The main thing there is it's done via using commercial routers with different firmware. Yeah, I don't remember why the power supplies showed up in the other digital mode thing, but it was part of the takeaways. The main thing is I mean, all of these radios, whether it's in your car or your base station, nowadays require a separate power supply. Old tube types, in fact, most cases, you plugged in the wall, ran off 120 volts. Today, you need a power supply, so you need to make sure that you get a power supply that can handle the amount of power. And because transmitters are not 100% efficient, you need to have at least twice. So if you've got a 50-watt transceiver, say in your car, of course, there you're operating on a battery. Let's say it's a 50-watt transceiver, and you're, out in a park. You got a power supply with it. You need at least 100 watts to operate that 50-watt transceiver, and probably more like 125 or 150, depending on how efficient it is. In order to do any of the digital modes, you need to be able to connect your computer up to your radio. So you're going to have a connection between the receive audio and the transmit audio on the radio and your keying input back to your computer. So you would normally connect your computer input to your transceiver output, and your transceiver input, to your computer output. So you always want to connect an output to an input. An output to an output doesn't work,
Right.
and an input to an input doesn't.
Yeah.
And most of the modern ones, you can hook up with a USB cable between the computer and the radio, and you get virtual audio channels and keying. You just have to figure out what the correct port is on the computer that your computer is seeing. But if you don't have a radio that can take a USB input, then you actually have to use the physical connections, which used to be RCA type cables. You can also get some little external boxes. I can't remember the name of it now. It's not a Rig Runner. Rig Blaster, I think.
Mm-hmm.
And it has a sound card in it, so you can connect USB to this little box, and then connect that to your radio if you have an older radio that requires the separate input and outputs. Noise prevention. The best way to counteract noise if you're picking it up is to use ferrite beads on all of your cables, microphone cable, speaker cables, USB cables, any cable. You can even put them on coax cables. Grounding is another big thing. You want to make sure that you connect all of your equipment together to a single point ground. You don't want to connect things together in a daisy chain. You want to connect each one individually to a single point ground. Can be a piece of copper pipe mounted on the wall, or a flat copper bar, or something like that that is a very large and thick surface area, so it looks like it's a single conductor. And that needs to be connected through either a flat copper strap or really heavy gauge wire to your ground outside your shack. Also, when you connect to ground rods, any of these things where you're doing it for lightning protection, you want to make sure that you're using either a welded connection or a compression connection. You never use solder. Solder would instantly vaporize when you get a few thousand amps running through it. For mobile operations where you're going to operate off of a car battery, seems obvious that you connect the positive power lead of your radio to the positive lead on the battery, and you do the negative either to the negative lead or to the chassis ground that the negative battery is connected to. It's usually a fairly heavy gauge braided strap going to the chassis. To determine how long you can operate off of a battery, say you're doing POTA in a park or QRP or something, you just divide the amp hour rating of your battery, say it's 12 amp hours, by your average current draw, which you have to estimate. So you're going to have, a small amount, maybe an amp or less when you're in receive mode, and quite a few amps when you're transmitting, but you only transmit for a short period of time, duty cycle wise. So you have to figure out what that average is, and then you divide that into the amp hour rating, and it says I can operate for 12 hours, let's say, if I had an average of 1 amp. When you're operating a transceiver, some of the controls that you need to adjust and work with is microphone gain. It's usually a setting in the radio, not necessarily a knob, where it probably was on an older radio. If it's set too high, you're going to get some overmodulation and get audio distortion. If it's set too low, it's going to give you undermodulation, so your signal will be kind of hard to copy. Most of them, I think, default around 50%. Probably better to lower it a little bit, kind of find out where the best setting is. When you're trying to do FM, if you don't have a fixed channel set and you're actually tuning it with VFO, if you're above or below that signal, you're going to get some distorted audio if you're not actually on the FM carrier frequency. And these are really oriented towards FM communications, where you can, if you have a keyboard or a virtual keyboard on your radio, you can actually put the frequency in and store it in the channel. Or you can just, like I mentioned, rotate the VFO knob. But putting it in a memory channel allows you to easily recall it. So you can have a bunch of like repeater or simplex frequencies stored, so it's easy to call them up. And you do that on either a handy talkie or like a VHF, UHF base station would have those same capabilities.
Gotcha. Yeah, I'm gonna get going pretty soon. I've got to go get my grandson.
Okay. I'll post it on YouTube.
Okay.
Halfway.
Are these also going to be on the Dropbox or in the Dropbox?
Yeah.
Okay. I know the other
Uh,
ones are. I was just wondering if it was like the condensed version, what you're doing now.
Yeah, I'll put this one on there.
Okay.
Like I said, I think it was 61 slides, so we're on 27.
Oh, wow. Yeah, we'd be here a while. Yeah, he's
Yeah,
only
what time?
4, so it's going to be, trying to keep him occupied is going to be kind of hard.
Okay. The other thing that most of them have, even the Handy Talkie, is a scan feature.
Yeah.
You can tune through a whole band, or even change, or actually go through different stored memory channels.
hmm
So you want to stop now?
Yeah, I'd like to, if you don't mind.
That's fine.
Yeah,
I'll try to get those on there today.
I appreciate it. While she's looking at rabbits, I'll be looking at slides. Hey, thank you for everything.